Hello guys, in this video we'll be looking at sampling and signal processing. We'll try to understand sampling in detail with all the mathematics behind it. In case you're wondering what happened to the letter M over here, you'll understand it by the end of this video. These are the contents of this video. First, we'll see some basic introduction. Then, we'll see sampling theorem, reconstruction, flat top sampling, natural sampling, and aliasing. So, what is sampling? Why do we need to study it? It's because of the immense usage of digital technologies. Sampling is like a foundation that made it possible for these technologies. Almost all real life signals are continuous. By continuous, we understand that it's an infinite amount of data, and it's practically impossible to store or process all this data. Let us first look at something called as ideal sampling. Let us consider a continuous signal g of t. This is just an arbitrary signal that we are using to understand this concept. Now we have something called an impulse train. So, impulse train is nothing but a sequence of impulses each separated by a time period ts. Let us call it delta tst. Now when we multiply this both signals, what we get is a sampled form of g of t. It means the g of t is no more continuous, it's discretized. We have only the samples of the original signal g of t. Mathematically, we can see it as impulses taking the functional value of the original signal g of t at different instants. Now let us understand what is sampling theorem. We assume g of t to be band limited as shown. The impulse train that we used previously will again be an impulse train in the frequency domain where each impulse is separated by fs, which is equal to 1 by ts. Also, the magnitude of each impulse becomes 1 by ts instead of 1. This fs is called the sampling rate and correspondingly ts is called the sampling interval. We all know that multiplication in time domain is convolution in frequency domain. So g of f gets convoluted with delta fs of f. What we obtain is the frequency domain representation of g bar of t, which is shown as g bar of f. This is nothing but g of f replicated and repeated uniformly at integral multiples of fs. Now, if you observe the spectrum, we can perfectly recover the signal if there is no overlap between these replicas. This means fs must be greater than 2 times of the signal bandwidth. For fs being equal to exactly 2 times of b is called the Nyquist rate, or correspondingly ts being equal to 1 by 2b is called the Nyquist interval. Now, when we do sampling above Nyquist rate, we can simply use a low pass filter to get g of f. Such a low pass filter will have a transfer function as shown below. Let's call it h of f. This is a rectangular function with ts as its gain. This gain of ts will suppress 1 by ts in the equation of g bar of f. Mathematically, we are only multiplying h of f and g bar of f, but that results in g of f and hence we can recover our original signal g of t. In the time domain, the inverse Fourier transform of h of f would be a sinc function. We can easily derive this using the standard inverse Fourier transform formula. Now, if we assume Ts to be 1 by 2b, that is, if we assume that the signal is sampled at Nyquist rate, we get the sinc function as shown in the figure. When we apply our sampled signal g bar of t as an input to this filter, the output would be g of t. Each sample in g bar of t, being an impulse, generates a sinc pulse of height equal to the strength of the sample as shown in the figure. Now, summing up all these sinc pulses according to the equation as shown, we can reconstruct our original signal. But the thing is, the rectangular function that we have used is only theoretically possible. Practically, it's not realizable. We can also infer this from the infinitely long nature of the sinc function. So, for practical reconstruction, we need to make use of a realizable system that can reconstruct the signal using the uniform signal samples, that is g bar of t. we may apply the reconstruction pulse P of t as shown here. Just like how the sync pulse took the strength of each impulse, in this case, P of t is used for that purpose. Let us represent this as g tilde of t. If we observe the equation, we see that we can write it as shown using the convolution property. This gives us a convolution between P of t and g bar of t. This simply means in the frequency domain, we multiply P of f and g bar of f, which results in g tilde of f. But to fully recover g of t, we will need to further filter this g tilde of f. For that, consider a filter e of f when multiplied with g tilde of f gives us g of f. Substituting the equation for g tilde of f, we see that when we fix e of f into p of f as shown for these frequency ranges, we can reconstruct our signal. These type of filters like E of f, which we require to fully recover the signal, are called equalizers. Till now, wherever we use sampling, we used impulses or impulse train, but impulse function is again only a theoretically existing function and cannot be realized for practical applications. For practical application of sampling, there is something called as flat top sampling. Here, instead of viewing each sample as an impulse, we say that for each sample, the sample value is held for some duration t. This is how it practically happens. We use a circuit called sample and hold circuit. To derive the equations for flat top sampling, we assume we have our g bar of t. This is only for derivation purpose and not the way it happens practically. Now consider h of t, which is a time shifted rectangular function. Flat top sampling can be considered as the output of a system with impulse response h of t, where we give g bar of t as the input. This gives us gf of t as shown here. In the frequency domain, the Fourier transform of h of t will be as shown, and that convolution becomes multiplication. We see that the spectrum of g bar of f gets distorted as shown due to the sinc function that is being multiplied. This distortion is called as aperture effect. We can recover our signal by using a low pass filter and an equalizer defined as shown below. Now let us see natural sampling. In natural sampling, we take the continuous signal g of t and multiply it with an impulse train where each impulse is a rectangular pulse. This gives us gn of t. We can write s of t as shown, and by now you should understand how the math works. It's very similar to our previous derivations. The thing to observe here is that we take functional value of sinc at that particular instant instead of the whole function like we did in the flat top sampling. This will ease the process by not demanding any equalizer function, and only a low pass filter is sufficient to recover the signal. Till now, we have considered that the sampling rate is above or equal to the Nyquist rate. But what if this condition is not met? This leads us to the topic aliasing. The word alias in English means to give another name, to conceal one's identity. This analogy can also be seen here. When we sample a signal below Nyquist rate, in the frequency domain, those replicas get overlapped and we cannot recover our signal. If we try to filter it using a low pass filter as we did before, we get a signal that is completely different. This process where we get a different signal altogether is called aliasing. If you go back to the first topic we have discussed, I mentioned that we assume the signal g of t to be band limited. All practical signals are time limited, and a signal cannot be time limited and band limited at the same time. This means our assumption does not hold, and our signal in frequency domain has an infinite bandwidth. We saw that all the sampling methods produces replicas in frequency domain. Now that we realize the bandwidth is infinite, the overlap of replicas is inevitable. This leads to aliasing no matter what is the sampling rate. If we decide to proceed without bothering, then we get a distorted signal. But what if we filter our signal even before sampling and in such a way that we manage to keep most of the information? Of course, we lose some information, but we are saving it from double damage because now the replicas don't overlap. In this video, We have seen sampling and its implementations. We tried to derive theoretical and practical concepts behind sampling. We now understand how powerful sampling is and its importance in modern communication systems. Thank you for watching this video.